Okay, so today we're going to talk about hypothesis testing, which is an important part of statistics, and it's really just an extension, as we're going to see, of our natural desire to understand the world around us and kind of establish what's really going on, or understand what's really going on. So first of all, what's a hypothesis? It's an idea that we want to test. It's the idea that motivates an experiment or an investigation. Now in statistics, in order to test a belief, we're first going to identify two different hypotheses. The first is known as the null hypothesis. This is your currently accepted belief or your default assumption. This is your sort of status quo, so to speak. And we denote this with H sub 0. This is a symbol for null hypothesis. The second is your alternative hypothesis. This is denoted by H sub A. This is your suspected claim that challenges or attempts to replace your null hypothesis. Okay, so this is like your uprooting sort of belief. So once you've defined clearly what both of these are, you go out and collect data, and then you're going to use that data to evaluate the validity of your null hypothesis. Okay, so let's take a look at example 1. So let's suppose you're trying to study the amount of actual water that you get in a typical 16.9 ounce water bottle. So they're often advertised as coming in this size. There's a company, let's say, whose water bottles you buy regularly. They advertise their bottles as containing 16.9 fluid ounces of water on average, but you suspect that there's actually less than that. So in this case, the null hypothesis is going to be your base claim, which is made by the company, that there are 16.9 fluid ounces of water in each water bottle on average, right? We know it's not going to be identically 16.9 every single time. Now, your alternative hypothesis is your suspicion or your challenge to this claim. So you're going to say there are less than 16.9 fluid ounces in each water bottle on average. Okay? And this has now defined the structure of your hypothesis test. Okay, so where do we go from here? So to actually now test a null hypothesis, we're going to try to establish evidence against it. So we can perform what's known as a test of significance or a hypothesis test. Now, we're not ever trying to actually prove an alternative hypothesis in one of these tests. What we're trying to do is we're trying to refute the null hypothesis. So we're trying to refute the original claim. So therefore we have only two possible outcomes. Either we reject the null hypothesis, or we fail to reject the null hypothesis. Okay, so in the first case, you might say that your test was successful. You were successfully able to cast suspicion on the null hypothesis and reject it. In the second case, the hypothesis test was unsuccessful. Now, that doesn't mean that the success is a good thing necessarily, or that the unsuccessful case is a bad thing necessarily. It depends on how you structure your test and what you've defined each hypothesis as. Okay. So if we go back to our case of the suspicion about the water bottle company, once we've gathered our data and performed a significance test, depending on the result, we might have two outcomes. Number one, we reject the claim or the idea that there are 16.9 fluid ounces on average in each bottle. Or we might say we fail to reject that claim. Okay. So again, we're not trying to prove or establish either claim. Tests of significance are inherently tests of refutation. We're trying to refute that null hypothesis. Okay, so let's look at another example. Suppose you and your friend like to flip a coin to decide who pays when you go out to eat. Your friend has a lucky coin that they love to use. If the coin lands on heads, they pay. If the coin lands on tails, you pay. In the last 7 times you've gone out to eat, the coin has come up as tails every single time. Your friend claims that this is a perfectly fair coin, but you have your suspicions. Okay? So now if you're going to identify the null hypothesis and alternative hypothesis in this case, the null is going to be your friend's claim. The coin is fair or the coin is not biased. Either one. So this is your original claim by your friend. Your suspicion is that the coin is indeed biased. This is the alternative. We're challenging that original claim made by your friend. Okay, now suppose we actually go ahead and carry out a significance test. And this test finds that the past 7 outcomes being tails is just too unlikely to occur purely by chance. And you would determine this maybe by comparing it to some sort of threshold. So if the probability is below a certain amount, if it's, say, less than 5% or less than 1%, then we're going to say, well, this is a very suspicious result. Okay? And in that case, what should our conclusion be? If we think it's too suspicious of a result, well, we're going to actually go ahead and reject the null hypothesis. Okay, so we're going to reject the claim that the coin is unbiased. Now, this result could mean a lot of things in reality, right? So we're not quick to jump to conclusions in statistics. Even though we might believe this coin is biased, right? So we're rejecting the idea that it's unbiased. It's not necessarily that your friend is a cheater. It could have just been that they didn't know, right? Or it could be that they did know. In either case, that's beyond kind of the parameters or beyond the purview of our significance test. So that's not going to be part of our claim, ultimately, or our conclusion. Okay? Now, there's also the chance that we're simply wrong, right? All we did was calculate a probability and say that, well, we think this is too unlikely. But even if it's unlikely, it doesn't mean that's impossible, right? It's not impossible that the coin came up as tails every single one of the last 7 times, right? We've actually calculated those probabilities before, and we see that this happens in real life. Sometimes you might just get 10 tails in a row, or 12. Last lecture we talked about the gambler's fallacy, which the roulette wheel showed up as black 26 times in a row. Now that's incredibly unlikely, but it's believed to be a true result. So that's a true result that happened in reality. So it's certainly not impossible. Okay, so a hypothesis test or significance test is ultimately founded upon likelihoods, and it's not definitive answers about reality. Because of that, there is a small chance of arriving at the incorrect conclusion. So in our last example, it's perfectly possible that the coin is in fact fair. Now let's see an example where it's very important whether we're right or wrong. This can sometimes have some significant repercussions. So example 3. Consider a patient is undergoing routine screening for cancer. In reality, the person may or may not have cancer. The screening test may indicate a positive result, meaning the presence of cancer, or it may indicate a negative result, meaning the absence of cancer. So first of all, let's identify the null and alternative hypotheses. So our default assumption, right, this is just a routine screening procedure, we don't believe that the person has cancer. Right, so your null hypothesis is the patient does not have cancer. This is similar to we assume everyone's healthy until proven otherwise. It's similar to how in a court of law, you'd assume by default that a person is innocent until proven guilty. So this is our default. The alternative hypothesis then is that the patient does have cancer. Okay, so this is your potential suspicion. So just like I was saying before, it's not always a good thing to reject the null hypothesis in real life. In this case, hopefully we can fail to reject the null hypothesis and prove that the person does not have cancer. Our successful result is the failure to reject in this case, or a positive result, I should say. All right. So now what we can do is we can actually, so we want to consider, the cases in which we might be right or wrong with our hypothesis test. So let's consider all possible outcomes of this test. So this is a two-way table. On the left here, we've got the reality, the true case, and on the top here, for our columns, we're going to have what we believe to be the case based on the test result. So in reality, the person may not have cancer, or they may have cancer. Now the test may come out negative and indicate the absence of cancer, or it may come out positive and indicate the presence of cancer. Okay, so as you can already see, this is going to give us a bunch of different combinations for what might happen. Okay, so in the first case, the person does not have cancer and the test reflected this. So this case we call true negative. The person has been indicated as being negative for cancer, and that's true. They truly are negative for cancer. When the belief matches the reality, this is a true case. Okay, so your other true case is when a person has cancer and they are positively indicated for cancer by the test. So this is going to be your true positive case. Again, the belief, the positive test, matches reality. Okay. Now, we might also have a case where a person does not have cancer, but the test indicates that they do. So they've been marked positive, but incorrectly or falsely. So this is what we call the false positive case. And finally, a person may have cancer, but the test may indicate that they do not. So it has falsely marked them as negative, or classified them as negative. Okay? So to do a quick review of all of these cases, we've got true positive, This is when we correctly believe someone to have cancer. So our patient has cancer. Then we've got the false positive case, where we incorrectly believe someone to have cancer. And then we've got our two negative cases. We've got true negative, where we correctly believe someone does not have cancer. And then we even have the false negative case, where we incorrectly believe someone to be cancer-free. Okay, so naturally we're not concerned when the test is working correctly, when it's true positive or true negative. We're concerned when the test fails to work correctly. So we're concerned with the false positive and false negative cases. So in hypothesis testing, false positives are known as type 1 errors. False negatives are known as type 2 errors. And both of these are going to have a certain probability associated with them. Okay, so there's a non-zero chance of committing either of these errors and arriving at these wrong conclusions. Okay, so let's look at the same example, but consider it with some numbers. Okay, so we've got a little tree diagram here now. Let's say we had 1,000 patients coming in total. And now their true state, 10 of them actually have cancer. 990 of them do not. Now, patients from both groups are going to get the screening test. Of that group with cancer, let's say 9 are going to be indicated to be positive, and 1 is going to have a test that comes back as negative. From your second group, the people who do not have actually cancer, 99 come back as positive, and 891 come back as negative. So let's see if we can now identify what's going on in terms of true negatives and true positives. So first of all, of the people who have cancer, 9 of them are correctly identified. So this is the true case. And of the ones who do not have cancer, 891 of them are correctly identified as negative. So this is going to be your true positive case up top. This is your true negative case on the bottom. And then we've got these middle cases, where a person is falsely identified as negative. So even though that person has cancer, they're coming from the group of 10 with cancer, they may get falsely identified as negative. Or they may be coming from the group which is cancer-free, and they may get falsely identified as being positive. This is your false positive. Okay, so this is your type 1 error group, and right here is your type 2 error group in pink. So now the question becomes, how good of a screening test is this actually if it can get it wrong, right? So we see there's 100 people here who have been misidentified in terms of their disease. Okay, so this is like a real-life hypothesis testing mechanism. And you can actually evaluate these based on their type 1 and type 2 error rates. Okay? So because we know these tests can fail, we need to identify how effective they are in practice. And now this is a case where empirical probabilities are going to come back. So we talked about empirical and theoretical probabilities, and of course theoretical probabilities are superior in a lot of cases, right? If we're talking about flipping coins or, rolling a dice or something like that. But in real life cases like this, there isn't really a theory behind what this screening test, how this screening test works or how it identifies people. We have to go back to empirical probabilities. So this 1,000 patients, this is like our sample. And we're going to make calculations based on our sample. And we've got a simple formula here for accuracy. So this accuracy is going to gauge how powerful this test is or how reliable it is. And this is your number of people who are true positive and your number of people who are true negative. We're going to add them together. So essentially the number of people that have been correctly identified, and then just divided by the total. So in this case, we've got 9 people who are truly positive and 891 people who are true negative. This is coming out of our 1,000. So this simply comes out to 900 out of 1,000, or 90%. So that's not bad. Out of the 1,000 people that came in for a screening test, 900 of them were correctly identified for their condition. But 10% were not, so that's still 100 people who were misidentified. So this kind of thing can happen with real-life screening tests, and of course, they try really hard to get to levels like 96% or 97% accuracy and things like that, but a big part of that is also people who don't have symptoms shouldn't be going in for tests, because that can now skew your results and things like that. It'll increase the amount of people who are falsely positive or something like that, and that will detract from the accuracy of the test. All right, that's all for this lecture.